IB Year 11 exam, standard level paper 2. Question 1. Define the average, or define the term average bond enthalpy. The average bond enthalpy is the energy required to break a specific type of bond measured over a range of similar molecules. So energy required to break, we should say the average energy, because it's where it says average bond enthalpy here. Let's put the word average in there as well, because it's the average or mean, the mean energy required to break a specific type of bond measured over a range of similar molecules. We're going to highlight that in blue to show that we're answering the questions. Alright, so we've got the answers in blue. Part B. Deduce the balanced chemical equation for the complete combustion of butan-1-ol. Okay, combustion. Well, combustion means it's reacting with oxygen. So the first thing we put in is it's oxygen. There's O2. Let's put in an arrow. And what are we going to get? Well, carbon from the organic molecule here is going to make carbon dioxide, CO2. And the hydrogen is going to make water, H2O. This is true for all organic combustions. Let me just format that. O2, CO2, H2O. Formatted. Okay, now 4 carbon atoms in the reactant that's being burnt, so there must be 4 carbon atoms here, 4 carbon dioxides. On the left hand side we have 10 hydrogens, that must make 5 waters on the right hand side. Now we count up the oxygens, 4 O2s 8, 5 O's, 8 and 5 is 13, so that's 13 oxygen atoms. Well, there's already 1 there on the left hand side, so we need 6 more. Sorry, we need 12 more, so we need 6 O2. So our balanced equation is as written there. Okay, then we have to determine the standard enthalpy change for the complete combustion of butan-1-ol using the information from table 10 of the data booklet. Well, table 10 of the data booklet, let me just get the data booklet here. Table 10 is bond enthalpies and bond enthalpies, average bond enthalpies at 298. Okay, so what we have to do is we have to say how many and what type of bonds we've got in the reactants. So reactant bonds, a bit of a strange format there. Reactant bonds, well, we can see that there are 4 carbon atoms joined to 9 hydrogen atoms and an OH group. So first, let's have a look at reactant bonds. Well, CH bonds, there must be 9 of them. CH bonds times 9. That's going to be equal. So we look at the carbon-hydrogen bond enthalpy, and it's 413. So it's 413 times 9. I'm going to calculate that in a moment. What else have we got? Well, if there's 4 carbon atoms in a line, there must be 3 CC bonds. CC bonds times 3. And that equals, just pretty up a bit, CC bonds times 3. Well, each C single bond C is 347 kilojoules multiplied by 3, and we'll work that out in a moment as well. What else have we got? Well, we've got 1 CO bond, because we're joining the carbon to an OH group, times 1, and the C single bond O is 358 kilojoules. Time, just keep it the same shape, times 1. And last but not least, there's an OH bond. OH bond times 1, and that equals, the OH bond is given to us in the data booklet as 464 kilojoules times 1. So that will allow us to work out the reactants, the energy required to break up the reactants, apart from the oxygen. We've forgotten the oxygen. Here's the oxygen, 6O2. So we've also got to break these bonds up. So it's an O, double bond O, times 6. And that equals, well, O double bond O is, bond energy is 498. 498 times 6 equals. Alright, so it's a question now of hard slog, get on the calculator and work those out. 413 times 9 equals 3717. 347 times 3 equals 1041, and then 358 and 464, and the last one, 6 times 498, 498 times 6 equals 2988, 2988. What do we do now? Well, we just have to add them all up together to give a total. Total energy equals, okay, 2988 we've got plus 464 plus 358 plus 1041 plus 3717 equals, and that comes to 8568 kilojoules. Right, now this was just the reactants. On the right hand side we've also got the product bonds. So let's just scroll up a little bit and say products bonds. The products bonds are somewhat easier because there's 4 CO2. Now CO2 each carbon dioxide contains 2 CO bonds. So it's CO. There are 2 per carbon dioxide and there are 4 carbon dioxides, so we must multiply that by 8. Similarly, water contains the OH bond. Each water molecule contains 2. There are 5 water molecules, so we multiply that by 10. Alright, CO bond from the data booklet is 746 kilojoules. And the OH bond is, we've already used that, haven't we? So we've got it up here somewhere. There we go, 464. Alright, so it's 746 times 8 equals 464 times 10 equals, we can see that's going to be 4640. So we just have to multiply out 746 times 8, 746 times 8, that comes to 5968, and the total energy change here can be added up as well. Total energy equals 5968 plus 4640, 4640, and that comes to 10608. 10608. Now these are bonds that are being made, so they're all exothermic. So I'm going to put negative signs in here. These are all negative signs to show that it's exothermic. Okay, now to determine the standard enthalpy change then, using this information, well, what we do is we just add these two values. So we just come down here, and I want to just cheat. I want to say standard enthalpy change. I'm going to copy it here. Standard enthalpy change, copy, equals 8568 minus 10608. And that equals 8568 negative 2040 kilojoules. And there is the calculation for 3 marks. Quite a long calculation for 3 marks. Let's move on to the next question. Based on the type of intermolecular forces present, explain why butan-1-ol has a higher boiling point than butan-al. Well, butan-1-ol butan 1-ol is an alcohol. It contains OH. Whoa, what's happened here? OH groups which can hydrogen bond from molecule to molecule. This is intermolecular. But butanal cannot do this. It's an aldehyde. It doesn't have any hydrogen attached directly to an electronegative atom. Butanal has only van der Waals forces and dipole interactions. Of course, butan 1-ol has van der Waals forces as well. I will put here as well as van der Waals forces. Okay, remember everything's got van der Waals forces, but butan 1-ol has got hydrogen bonding as well. So we get our 2 marks for discussing those 2 issues. Next question. Question 2 then. Iron has 3 main naturally occurring isotopes using a mass spectrometer to investigate. Explain why a very low pressure is maintained inside the mass spectrometer. Well, you've got ions flying around. You don't want them bumping into air particles. That's right. So that there are no collisions with the air particles. That'll do for an answer. Another reason, perhaps, would also avoid getting false data from the ionization of air. So with that, there also it avoids ionization and detection of air molecules. So there's 2 reasons. Either of those would be worth your mark. Iron has the following composition by mass. Calculate the relative atomic mass of iron based on the data. Okay, right, so there's 3 isotopes, so the relative mass will be the average, the weighted average of the 3. So these are percentages, so it's 54, contribution from isotope 54 times 0.0595 plus 56, in brackets, 56 times, and the contribution 0.9188 plus 57 times 0.0217. We'll work that out. Taking a note that we're going to answer it to 2 decimal places in the end. Alright, so let's do a calculation. 54 times 0.0595 equals plus brackets 56 times 0.9188 close brackets equals plus bracket 57 times 0.0217 close bracket equals 55.90. 55.90, where 2 decimal places were required. So there's our calculation. Calculate the number of electrons in this ion. Of electrons, well, if we look up iron in the periodic table, the atomic number of iron, number Fe, is 26. So if the 2 plus is showing, therefore 2 plus iron has 2 less electrons, 24 electrons. On to the next question. Graphing is an important method in the study of the rates of chemical reactions. Sketch a graph to show how the reactant concentration changes with time in a typical chemical reaction. Show the rate of reaction at a particular time, show how the rate can be determined. Okay, so how does the concentration of a reactant change? Well, it starts off high, and then it curves down to, I'll just put an auto shape in here, so axes. Not likely. We'll start off somewhere up here. I'm going to put a little X. Well, I can't put a little X on here. It doesn't really matter. I'll draw a shape, shall I? That'll do me. An auto shape. There we go. An auto shape, and let's just drag it. We'll start off high. It'll end up low. And it will curve between the 2 points. Reactant concentration changes with time. This axis is going to be time along here. Okay, this axis is going to be the reactant concentration. It will be a curve. I don't think I can draw a curve on this. Change auto shape, can I? No. Not particularly versatile, this program. Alright, so the rate of the reaction at a particular time can be determined from the gradient. Alright, so we put in the rate at time t, where t is any time, equals the gradient to the curve. Okay, part B. A solution of hydrogen peroxide is added to a solution of sodium iodide acidified with hydrochloric acid. The yellow colour of the iodine can be used to determine the rate of reaction. So if we look at this equation, you'll see that there is iodine appearing on the right hand side. Okay, iodine is appearing on the right hand side here. I'm going to highlight it. The experiment is repeated with some changes in the reactant conditions for each of the changes that follow, stating a reason its effect on the rate of reaction. Let's have a look. The concentration of H2O2 is increased at constant temperature. Well, this is a reactant. You increase a reactant, it's going to increase the rate of reaction. So the rate increases. Do we need to explain it? There's 2 marks. It probably would do. Stating a reason. The rate increases because there are more collisions per unit time. The solution is prepared from a fine powder instead of large crystals. Well, it doesn't really matter what you make it from because it's the actual solution that's reacting. This has no effect. No effect. The solution characteristics are the same regardless of how the solution is made. Alright, so that's our 2 marks. Let's go on to the next question. Explain why the rate of reaction increases when the temperature of the system increases. Well, the main reason is there are more particles have the required activation energy. But also, there are more collisions per unit time. More particles require activation energy, so there are more successful collisions. There are more collisions per unit time. Okay, let's just highlight that one, blue, and move on to the next question. Hydrogen can be made by the reaction of hydrochloric acid with magnesium according to that equation. What mass of hydrogen is formed when 100 cm cubed of hydrochloric acid of concentration 5 reacts with excess magnesium. So this tells us that all of the hydrochloric acid is going to be used up. Alright, so first thing we need is the moles of hydrochloric acid. Moles HCl is the volume in litres, 0.1, times the molarity, 5. And that comes to 0.5 moles. So from our equation you can see that 2 hydrochloric acids make 1 mole of hydrogen. So therefore moles of hydrogen, moles of H2 created equals 0.5 divided by 2, which equals of course 0.25 moles. And the mass of hydrogen then is the moles times the relative mass. Mass equals moles times mR, relative mass. Well, the relative mass of hydrogen, H2, is 2, so it's 0.25 times 2 equals 0.5, 0.5 grams. That's easy sum for 3 marks. Question 5. Compound contains 38.9% by mass of iron. So it's 38.9. Divide it by the relative mass of iron, which is 56, and 16.7, sorry, 16.7 of carbon, divided it by 12 to get carbon. So this first one here is iron, second one here is carbon, and what must be missing here is oxygen. So the oxygen proportion is 100 minus those other 2 percentages. So it's 100 minus 38.9 minus 16.7, and that comes to 44.4. 44.4, and we divide this by the relative mass of oxygen, which is 16. Alright, so let's work our 3 sums out here. Our ratios. The first one comes to 38.9 over 56. 38.9 divided by 56. 0.695. 0.695. Carbon. 16.7 over 12. 16.7 divided by 12. That comes to 1.39. 1.392. I'm working to 3 significant figures really here. Sorry, it's 3 decimal places, not significant figures. 44.4 divided by 16, and that comes to 2.775. 2.775. Now the way to work out is now to divide through by the smallest number. We can see this is the smallest number, so let's divide everything by 0.695. Alright, so we put the 0.695 under the other 2 as well, and this comes to, obviously the first one comes to 1, the next one comes to, I don't know, 1. Well, you can see this by inspection really, 1.392, 1.392 divided by 0.695, and that comes to 2.00. It comes to 2. And the next one, 2.775 divided by 0.695, and that comes to 3.99. Well, it comes to 4. 3.99 is as close to 4 as you're going to get. So our empirical formula then, the empirical formula is equal to Fe C2O4. Format those, put that across, and let's colour them in so we can see it's the answer. And that's for our 3 marks here. Alright, 1 mole of this compound is decomposed at heat is heated, it decomposes to give 1 mole of iron 2 oxide. Alright, so let's put our chemical in down here. This is our chemical, Fe. This is going to be heated, and it's going to give, wrong way around, it's going to give FeO. Alright, so what else can it give? Well, you've taken one Fe, one out, that leaves C2. That gives 1 mole of carbon dioxide, we're told that as well, plus CO2. And what else is left? Well, carbon's left, and an oxygen's left, so the other gas must be CO. Just a case of counting up that's left. Identify this other gas. Right, okay, so that's a quick question. And move on. Propanol is the structure. Gaseous propanol burns as shown in the equation. Oh, this is another one of putting together all the bonds. Well, here we've got 1, 2, 3, 4, 5, 6 CH bonds. So that's 6 times CH. CH is 6 times 413. 413 times 6. That comes to 2478. And 2 CC bonds. 2 times CC equals each CC bonds 347. 347 times 2, 694. What else have we got? 1C double bond O. 1 times C double bond O equals C double bond O is 736. 736. And don't forget there's 4 oxygens. So there's also 4 times O double bond O. O double bond O is 498. 498 times 4 comes to 1992. So the energy change when all the bonds in the reactants are broken, total energy change equals, well, we're breaking the bonds, so it's positive, so it's plus, and we just add those together, 1992 plus 736 plus 694 plus 2478, 2478, and that comes to 5900, 5900 kilojoules. We'll highlight that to show that we've done the working. I thought so. I thought they might ask us for how many the bonds in the products. Alright, well, what have we got? Let's just take the products out just so I can remember them down here. The products are the... Oy, didn't get that at all, did I? What's happened there? Why didn't I copy that? Copy. These are our products here. Alright, so we've got 6 OH bonds. And an OH bond we're told is 464. 464 times 6. That comes to 2784 kilojoules. We've got 3 CO2, so we've got 6 C double bond O. And that comes to, well, C double bond O is 736. So it's 736 times 6, 4416 kilojoules. So the total bond energy equals, in this case we're making the bonds, so it's negative 4416 and 2784, 7200 kilojoules. Make this nice and blue. And the enthalpy change for the complete combustion will be the difference between those two. So it's plus minus, what do we get for that? That's going to come to, with a calculator, 1,300 minus 1300 kilojoules. That's the end of section A. I'll go to section B in a moment.